Okay, so last class we studied about hard disk drive. Today we will study in very brief about solid state drive or flash drives. We'll just look at what these are and how do they operate at very top level. Okay, there's not many good references that are available. I have taken contents from CS162 of Berkeley and few resources from internet. Okay, you can feel free to use any website or book for your own study. All right, so let's look at what we studied last in the last class. Was in detail we studied about magnetic disk, and then we also looked at what flash memories are in principle. Okay, then we look at various you know characteristics or various ways we can compare RAM versus hard disk drive versus solid state drives. Okay. Note that word solid state drive. It means that drive means actually it works similar to HDD. Its very purpose is almost it is the same, to store data that can be retained. Okay, unlike RAM. So this is persistent memory. Okay, and we have compared hard disk drive versus SSD uh, for size, cost, power, latency, speed, etc. And we saw that hard disk drive is still cheaper and it has more data. I mean, in a disk can store more data than correspondingly for SSD. And the read speed of SSD is much faster than that of HDD. Okay. Read all right, and bandwidth of SSD is much higher. All right. So we have also compared here the two. So one great advantage of SSD is that first thing is that it's faster in nature. Key and second is that consumes less power. Third is its bandwidth is also high. Okay, latency and bandwidth are in some way connected, but bandwidth says that how many bytes of data you can read in a unit time, right? Okay, while latency tells us that how much time each operation will take place. All right, basically bandwidth also captures the fact that how many parallel transmission that can happen uh, in a unit time, right? So the way memory is organized or limitations of its design or architecture is also reflected through bandwidth. Okay, and then we have compared SSD versus HDD, and we have seen in that in year 2026 is expected, it could be earlier too, that SSD will be cheaper than hard disk drive. Okay, so this point here, we can see that okay, here we can see that cost of SSD will drop. In terms of shipment or amount of or terabytes of flash memory being manufactured is already overtaken hard disk drive. Reason is that SSD or flash drive is being used in many devices where HDD cannot be used. And one example is your digital cameras, right? Okay, if you have SLR digital camera or any ordinary digital camera, then it has SSD or flash drive, right? And these were very expensive. Now it's becoming extremely cheap. Okay, I mean earlier I had one Nikon SLR, digital SLR. Earlier the chip capacity was so less, SSD capacity was so less that it could hardly store, around 500 images in when resolution is high. Okay, but today we have very high capacity SSD chips available. So camera is one such example. Mobile phones are others, and many places, right, where you can't think of, having uh, a hard disk. You can put flash drive, right? So all this, for example, when very small devices, okay, okay, which can be placed anywhere, like your, like home camera or even refrigerator or washing machines, all of them now will have flash memory, because it's very convenient. All right. uh, so now the point I wanted to say that ki SSD has more applications. I mean, it can be used in more number of devices and applications than hard disk drives. Okay, and we at this point we already discussed. So in future, we'll not be surprised that none of the laptops will have hard disk drives. Okay, all right. So now let's look at how it works, etc. Okay, any question up to this point? No? All right. So let's move ahead then. Okay, so this is most promising solid state storage technology. When it says solid state, it means that it does not have a moving parts like in hard disk drive. Okay, so there are two types of flash memory, NAND type and NOR type. The one which is becoming de facto standard is NAND type. Okay, NOR type is has some properties which are unique, like these are byte addressed. Even individual bytes you can address, like in case of RAM, but they are extremely expensive. So while NAND flash is page address, minimum unit that you can read or write is page. So the technology is cheap. So then we can say that, excepting in very special circumstances where NOR is used, all other instances, okay, it's only NAND flash that is used. So we can say now NAND flash is the de facto, and discussion henceforth will be around NAND drive. Right? So uses are many. We have already discussed this. Okay, so whatever we see in camera or the stick that you buy, memory stick, or that goes into USB, all are based on NAND memory. Okay. So here, however, there is a restriction here that each cell, or each, we can say, byte or whatever, cannot be written and deleted independently. So this restriction we will uh, discuss later. While in NOR gate, each cell can be handled independently. All right. So this is a flash cell for NAND gate. Okay, and if I'm sure you would have done a course on, what do you say, electronics, how chips are manufactured, etc. Possibly. So like MOS transistor, etc. Then you can make out something, right? Uh, so here the flash cell store data in a floating gate by charging at high voltage, and charge remains there. Okay, so it means that encodes bit by trapping electrons into the cell. Whether charge is there or not there gives you whether there is a store, there is a bit is 0 or 1. All right. Okay, So normally we have two levels, right? Either charge is there or not there. So the electronics that you use has usually very simple encoding. Okay. However, here later versions of flash that came out has multi-level cells, where many bits can be stored in a cell by differentiating between amount of charge in the cell. Okay, so normally in single level cell or ordinary cell that we have been using in other applications also, or ordinary electronics also, is usually two levels, right? Either charge is there or not there. Okay, so basically single bit can be stored. Okay, while in multi-level cells, how much charge is stepped, that defines whether different levels, and we can encode. So instead of one bit, we can encode 2, 3, or even 4 bits. It means that for 2 bits it will have 4 levels, for 3 bits it will have 8 levels of charges. That can be so so basically if charge is there, it can be measured at what the amount of charge, and based on that can find out whether 0 is stored, or 1 is stored, or 1 0 is stored, or 1 is stored, and so on. Okay, so multi-level cells are cheaper to manufacture. Okay, however, they wear out faster than single level cells. All right. Okay, and they are more fragile. Fragile in the sense that stored value can be disturbed by access to nearby cells. If you make changes in nearby cell, then it may impact neighboring cells. Okay, so this is at the top level. We can understand that flash usually comes in single level cells or multi-level cells. Now one exercise you can do is that the flash memory stick that you have, look at its details. You can find out on internet the details and find out what kind of flash memory stick you have. Okay, what is its capacity, and look at the specification. You will now can relate with it, whether single level cell, multi-level cell, it's an NAND type or not type, or many other parameters, right? Okay, any question? Okay, all right. Okay, so we just discussed single level or multi-level cell. This is within a cell. Okay, but cell can be made. See, most of the ICs that we fabricate is actually 2D technology. Okay, now we can manufacture this in 3D also. Okay, so here memory cells are stacked vertically in multiple layers. We are talking multiple cells. Earlier we were talking about within a cell there can be multiple levels. Now these cells normally in most, when if you study IC technology, these are placed side by side. Okay, not one on top of the other. Okay, so now we can put these stacks of cells one after other, right? So it basically it will go in a horizontal as well as in vertical direction. All right, so now so new technologies are coming up. All right, so it has lower cost, obviously, right? So this is very latest development, maybe just 3-4 years back or so. Okay, all right. So now see, RAM is very, when we look at RAM, it is byte addressable, and structure is very clean, right? Any byte can be addressed, and there is a very well-known addressing techniques for that, right? Possibly you would have studied that in your digital electronics course. Okay, while here there is little complication, and that we'll look at. Even with HDD, there is some complication that we'll have to move the head arm to particular track, and then this will rotate and will start reading at a particular point, the sector in which you want to read. and whole sector is to be read. Okay, similarly, there are some restrictions here, and we'll see what are those restrictions. However, before that, let's look at the storage hierarchy. Okay, of course, we have flash. First on top is a chip, or we can also call it, there's one more word for that, we'll come to that. I think it's called, just a minute, package. Okay, instead of flash chip, we can also say package. A package contains several banks. Okay, so one more hierarchy we can put in, that a package contains several dies, and each die contains several banks. But anyway, so package and die, let's treat as a single term right now. However, a package, a chip, can contain multiple dies. We'll look at the diagram later. And the next level is a bank. Okay, so and then each bank consists of multiple blocks. Okay, so and each block contains multiple pages, and each page contains multiple cells. Okay, so we have a plane, we have a chip consists of number of banks, each bank consists of number of blocks. Okay, and each block consists of number of pages. All right, so the numbers given here is as follows. Each block consists of 64 to 256 pages. Each page consists of 2 to 8 KB of cells, and each cell contains either 1 bit or say 4 bits. Okay, this is another way of looking at it. Okay, so we have a die. Okay, we can, okay, so basically, let's assume that we have a chip which has just one die. Okay, so this is a die. Okay, the one which is shown here is a die. This is one die. One die consists of two planes. So there are two planes here. Okay, and each plane consists of certain number of blocks. Okay, the blocks is shown as a gray one. So this is a block, the one which is shown here, or the next one, this is a block. And each block consists of number of pages. So number of blocks here in a plane, for example, the first plane, this plane is 3, 6, 9, 12, 15, 18. There are 18 blocks. Okay, there are two planes, each plane has 18 blocks, and each block has 10 pages. Okay, the one shown in green is page, like here, these are pages. Okay, and each page will have certain number of cells. Okay, so this is the structure. Okay, all right, so each die contains one or more planes. Let's assume right now chip has just one die. Okay, identical okay, so number of planes are usually one or two. So here we have two planes, first and the second. Okay, so they are identical. Okay, this and the other one, and identical operation also can take place. Okay, not always, right? So identical concurrent operations can also take place in each plane, of course with some restriction. And each plane consists of a number of blocks. Okay, so there is one block here that we have seen, the block here, for example. Okay, this is the smallest units that can be erased. Okay, so if you have to erase it for rewriting, then everything in the block has to be erased. Now this is in contrast to RAM, where even single bit can be erased, or what do you call, say, data can be rewritten to that. Okay, so okay, and each block contains number of pages. As we have seen, the smaller one is a page here, the one, for example, here, and this is the minimum unit that we can read or write, that can be programmed. Okay, so now look at the, what do you call that, details. So write can take place on a page. You cannot just write a byte on a page and then again change another byte. All the bytes in a page have got to be changed together. Okay, all right. An erase operation takes place in a block. So basically writing, if you have to do writing, you will have to, at so many locations, this needs to be rewritten. 8 to 16 KB kilobytes is the size. For example, is 8 KB is the size. So all 8 KB locations have to be written, okay, at a time. And when we are erasing, why this word we have not used this earlier, right? Erasing. Okay, so basically there's a difference. In a RAM, for example, you can whatever is the data in a location, you can overwrite over that. Okay, while here first it is to be erased, like a slate. I don't know whether you have used a slate in your childhood, but the black color slate on which you write and then clean it off completely. So complete cleaning it off, right? So the erase operation will when any location is to be written, that it is to be written in terms of number of pages, but when it is to be, but in order to write, first it has to be erased. Whatever written earlier is to be erased, and that erase operation will take place only in a block. It means that even if you have to write, for example, something in a page here, the whole block, which is this one, right, the one here, the one which I'm showing here, I don't know whether you can see the color, all these are to be erased. Okay, so you can see that even if to write 8 KB block, you'll have to erase almost like 4 MB area, right, or locations. And a block need to be erased before it can be programmed. Program means written. So now you can see that read operation can take place on a page, write can be done on a page, but erase has to be done on a block. Okay, any question? All right. Okay, so now from this you can find out this really interesting, right? How does it work? So you cannot do any update operation on flash location. And you like in a RAM, you may want to change a addressable unit, which is a byte in most of the cases. Then you cannot change just one byte. Okay, update means that you cannot overwrite it. Okay, so there is no undo or rewind mechanism for changing what is currently in place. I mean, you have written something in location and you want to undo it and write something else, that's not possible, right? The operation is just erase and then rewrite everything. Okay, so erase operation on a flash chip clears the data from all pages on a block. So basically a minimum unit that you can delete is a block. Okay, so what happens if some of the pages contains active data, for example, so you want to delete this page, erase this page, right, and maybe 2 pages, but all other ones, like here the remaining 6, for example, contains valid data. So it means that you cannot erase this. Okay, and if you need to write this data rewrite and it is in continuation with the data here which are valid, then you have to move everything to a new block. Then you can write, for example, the 4 which needs updation and remaining 6 are the old ones. You'll have to copy that data into new block. Okay, got it? Any question? No?
No, sir.
All right, okay. So now this again with different way the same data is presented. We have concept of as we have seen, plain or bank. Okay, now here we can say in bracket blank bank. Okay, so or we can say plain here. Okay, so there is a plain, then block, then page, and within page where we have cells. And the same thing we have, same data is presented here. Okay, this is another view. Okay, so we have a block. Okay, and within block there is a page which is projected as this one. Okay, and each plane contains so many blocks. Right, each of it means that each of this unit will be something shown here. Okay, and each one of the page will so many number of bytes. Okay, all right. So again, same thing, erase operation before a block can be written, it has to be erased. Okay. Okay, so when you have to erase, it's setting it to logical 1. Anyway, it doesn't matter. We'll not getting into actual coding of that. In order to write a page, so you'll have to write on a page, full page, and tens of this will take tens of microseconds to hundreds of microseconds, and reading a page will take tens of microseconds. Okay, so writing takes a lot of time. Okay, however, in order to write, you'll have to find a available page. That's one restriction. Okay, even few bytes are to be written, it's written onto a full page. Okay, next restriction is that if you have to delete a page, you have to actually delete the whole content of the block. All the pages are to be deleted. It means that remaining ones need to be copied somewhere. Okay, or don't delete. So the one way is that you can suppose this is a block consists of 2 pages. Okay, and something is to be deleted, just mark it invalid. Okay, and the other page can be used. So deletion, basically this movement of data, for example, if the whole block is to be deleted or erased, then this has to move, and this contains valid data, this has to move somewhere else which is free. Okay, so that's another possibility. All right. Okay, all right. So now here you can look at the data, how much time it will take. Flash drive has 4 KB pages, 3 milliseconds to erase a block. Erasure block is actually the one which is to be erased and rewritten. Okay. Okay, so and 500 KB erasure blocks, each block has 512 KB and 50 microsecond to read and write a page, and from that you can calculate how much time per write will require. So it turns out that per write, which is to each page will be approximately 15.8 millisecond. All right. Okay, so you can compare this with in case of a RAM or in case of a disk. Okay, all right. Okay, so now let's look at from different perspective. Okay, writing data is a complex thing. Okay, because it has to be done only on empty pages. So if a block has an empty page, a data can be written onto that. Okay, and it is all right. So erasing a block takes approximately 1.5 millisecond. Okay, so now in order to do this, controller has to maintain pool of empty blocks by combining or cleaning up or garbage collection all these pages that were in use, that have to be deleted, and something that can be moved out. Okay, all right. So that operation that controller has to do, and it's a lot of work. Okay, for example, if this all is available, okay, this block is available, and 4K data, one page is to be written, and since all pages are available, it can be written here. Okay, now let's assume that another page comes to be written, it can be written here and so on. Okay, all right, this is simple. Okay, so let's assume that we initially everything is free, and this is a block, and which has 12 pages, and then we get data A, B, C, D corresponding to 4 pages. So these can be written here. So remaining are free now. Okay, all right, simple. Okay, and now the data comes E, F, G, H, A dash, B dash, C dash, D dash. So now enough space available. So E, F, G, H, A dash, B dash, C dash, D dash corresponding data can come here. Okay, now next thing is that A, B, C, D is to be marked obsolete, because all right, so I will just this way, just a minute, let me correct it. Okay, so initially ABCD is there. Okay, and then EFGH comes. So EFGH can be written here. Okay, now the next version of we have to modify something in this page, the second page, third page, and fourth page, which will say that A dash, B dash, C dash, D dash. Now instead of modifying it here, okay, this, because we cannot do that, there's no modification operation allowed, because this has to be cleaned up, erased, and in order to erase that, everything is this block is to be erased. It means all these ones will also be erased. So now instead of that, we can mark ABCD which were there earlier, which are now shown as in a light gray color. Okay, so these are all marked as obsolete, and new data, modified data, can be written here, A dash, B dash, C dash, D dash, in this space. Okay, is it okay? Okay, so now controller has a important function of garbage collection. Okay, and it's obsolete pages by copying valid pages to new blocks. Okay, so what happens is that the now for example this is free. Okay, so now it controller will see, if suppose let's assume that some other block is available, okay, which has some data, for example, valid data, okay, then it can make this block, complete block, available by moving the data which is valid here to this block, okay, like the one shown here, and this can make this block free. So everything can be erased and then rewriting can happen. All right. So there is some challenges here. Write and erase cycle requires high voltage. Okay, and this may damage memory cells and limit SSD's lifespan. Okay, and controller uses something called wear labeling. Okay, so controller uses error correcting code and wear labeling. So error correcting code we know. Okay, most of the memory chips, and we have seen use of it, right? Even in hard disks we have error correcting codes. What is wear labeling here then? Okay, I don't know. Okay, so wear labeling is basically movement of page, and actual is more of a see what may happen is that actually we'll come to this term little later. Okay, uh, I think it's anyway. So basically what happens is that if we are, see, one restriction with flash is that the number of times this erase and write cycles, number of times this erase and write cycles that can be done, or number of cycles are limited. Okay, usually 1000 to 10,000 or something like that. This number may be changing. Okay, so now if the same place we use, right, same area of the memory we use, or same page is being used say 1000 times, because let's assume that you keep doing these write operations, okay, and corresponding block is cleaned up very often, and then same location is used for different write operations. Okay, so what may happen is certain locations, certain pages may be heavily used while other pages are not used at all. Okay, so the one important role of this controller is also to, when writing is evident, use different parts of memory that's available. Okay, all right, so that it means that now on an average each page will be used less number of times, or there won't be heavily used part of flash memory. Okay, all right, any question? No? All right, and we can calculate latency as queuing time. There are multiple operations, from multiple processes, they have to be queued up. Okay, and then controller time. Now controller has to be very intelligent here. It has to find a free block, etc., and the transfer time. Okay, okay, the bandwidth here, calculation of bandwidth is slightly different. So we'll have to see whether it is a sequential write request or random write request, and availability of empty pages, etc. Okay, so rule of thumb is that writing is 10 times more expensive than reads, and erasing in 10 times more expensive than write. So erasing takes maximum amount of time than writing and the reading. Okay, all right, any question? Now this is the architecture. Reading, of course, we have already done. Minimum unit for reading is 1 page. We have already done it. Okay, just a minute. All right. Okay, so this is the architecture. Okay, so one architecture is as follows. I mean, there are of course modification to this as well. So there's a flash controller, which is very important. This of course is nothing but, what do you call that? Maybe this is nothing but, number of banks put into a plane into a die. Okay, or a chip we can think of, single chip. Okay, and it's connected to a controller. And of course, there are other things like buffer manager. If there are multiple requests coming in, it can be buffered here, and there is an interface with DRAM. Because whatever is read has to be there before transfer somewhere, right? So even for example, disk drive HDD will also have some RAM available. All right, so now just before going into architecture again, let's see the flash durability. So number of cycles that it can endure, that's erase and write cycle, or this called erasures, is usually between 1000 to 10 raised power 3 to 10 raised power 6. Okay, or this one way, so many times you have written onto the flash, or you kept the flash unused for certain number of years. Okay, or number of nearby cells are read, because even reading in nearby cells impacts the cell. So to improve durability, we use error correcting code, ECC, which we call in short. And then we have seen that okay, wear leveling is another thing that is not mentioned here. Okay, and third is that management of defective pages and block. So some pages may get defective. Okay, and if there is a defective page, first thing it is to be detected there is a defective, and secondly it is to be managed. It means that it will not be used. Okay, similarly a block may become faulty, then this controller can avoid this use of that block, right? All right, and another thing is they spread the updates to, okay, so if there are certain locations are heavily used, okay, basically hot logical pages to spread uniformly. So logical place is a concept of address space, right? So some logical addresses are used very heavily, and they are mapped to certain physical locations on flash. Then this mapping can change often, such that many pages can be used, many physical locations can be used for same logical position, right? Or same logical page. All right, okay, so let's there's another 10 minutes and we'll close. This is SSD architecture, that's very similar to the one we have seen here. Okay, so we have here what do you call that, various you can represent it anyway, I mean maybe blocks or something, but maybe planes. Above block is what? Okay, plane, right? Yeah. Okay. All right, so we have just a minute, we can have many chips or planes, whatever, and then we have RAM, and then a flash controller. Okay, all right, so this thing we have already studied, that the minimum unit that is to be erased is a block. So if you have to do rewriting on a location in a page, okay, then whole page is to be rewritten either in the same block or another block. All right, okay, all right, so the one more, so this controller can also So new version of controller has this solution that's called flash translation layer. Now we have seen there are a lot of things it needs to do. First thing is that it has to collect garbage. Let's assume there is a block, only in a block only one page is used. Okay, or maybe half number of pages are used. Okay, then if the remaining is to be utilized, and then the process requires more number of pages than that's available, then something that's valid can be moved somewhere else, that we have studied earlier, right? So all this intelligence can come into fresh translation layer, FTL. Okay, the first thing it does is that it exposes a logical linear address into the pages to the host. Okay, so at the higher layer we have concept of blocks. Okay, so and we have seen that the numbering is linear numbering, 0 1 2 etc, and then it has to be mapped into physical pages, right? So this mapping is done by FTL. And second is that this FTL keeps track of actual physical locations of pages and perform the translation. Fine. And it transparently performs many functions for performance and durability, like we have seen wear leveling and many other things, right? Okay, this is the same thing depicted here. So the job of translation layer is that map logical pages to physical pages, the first thing that we have already discussed. Okay, this is the same thing, logical to physical mapping. Bad block management. Okay, if some block becomes faulty, then it's to manage. Wear leveling, assign writes to pages that have less wear, which have not been used. Okay, error correction, we have seen each page physically has few bits for error correcting codes. Okay, see, if now we can also use a concept like we use in page tables, that if many logical pages can be mapped to a single physical page. Similarly here, many logical pages with the same data can be mapped to one physical page, because translation now is also being done inside in FTL. Okay, garbage collection we have already seen that. So clear still data and compact pages for fewer blocks. Okay, also it can do some intelligent things like write ahead logging. We keep collecting data and write it together. Okay, it can also do caching and prefetching, etc, right? I mean, if similar to in disk also we do caching and prefetching. I mean, for example, user program wants only a byte, it's very likely that next byte also be used, then and maybe one block, then next block will also be one sector, the next sector may also be used by process. So this can also do caching and prefetching. All right, this is just a diagram, shows various types of SSDs like SATA SSD, SAT SSD, USB thumb drive, and micro SD. Micro SD usually goes into, where is the camera, for example, or maybe your mobile. All right, so that's all. So advantage of SSD is it's a low latency, high throughput, no moving parts. It means higher reliability and read at very high speed in comparison to disk. Cons are that currently its capacity is lower than hard disk drive, but just another 3-4 years it will be the same, and it's changing, technology is changing very fast. Says compared, oh, is expensive compared to hard disk drive. Okay, again after some time it will be cheaper. Okay, and it has asymmetric block write performance, right? We have seen that reading and writing, you know, page has to be erased, and in order to do that, whole block is to be erased. Okay, and lifetime is limited, but usually enough. I mean, it's 10, 11 years, it will go for the normal usages. And again, this technology is changing very fast, so maybe very soon we'll have much higher reliability. Okay, any question? No? Can I ask question now?